We're going to continue on in Unit 2 and discuss covalent bonds, shared electron pairs. So we've been talking a lot about ionic bonds already, and what type of atoms typically participate in ionic bonds? See if you can remember. So remember, ionic bonds have charges. So ionic bonds involve a metal to a nonmetal or a polyatomic ion. Other atoms that are bonded together are held together a little differently. And so covalent bonds are an example of that. They don't gain or lose electrons, they share electrons. And that's what we're going to be talking about now, covalent bonds. Now remember, with ionic bonds, I just want to bring this up for review. Metals lose electrons, nonmetals gain electrons. Okay, so the definition of covalent bonds is the sharing of electrons to give each atom an octet. So the sharing of electrons to give each atom an octet. Typically, well, all examples of covalent bonds are between nonmetals and nonmetals. So here are some examples of molecules that have covalent bonds in them. So water, ammonia, and methane. And there's a section in your book that discusses this. So water is H2O, ammonia is NH3. These are the molecular formulas. Methane is CH4. In the Lewis structures, or electron dot diagrams for these, I will go over with you so you get an idea of what covalent bonds are. So water, the central atom in water is oxygen. And the way I've drawn this Lewis structure, I have the bonds as a line. These are the shared electrons. So each one of these represents 2 electrons. So that equals 2 electrons. You can draw your Lewis structures any way that makes more sense for you. Sometimes it's nice to draw the electrons involved in a bond as a line, so you see, okay, I have 2 bonding pairs, 2 lone pairs. You know, that especially will help with the geometry that's coming up. So when we look at water, if you count up the electrons around each atom, you should see an octet. And let's do that for oxygen, which is 2, 4, 6, 8. So oxygen has an octet. That's great. It wants an octet. Hydrogen, on the other hand, just has 2 electrons around it. 2 electrons. That's great for hydrogen. Hydrogen doesn't like too many electrons. If you remember, hydrogen is a minimalist, and it just needs to get 1 electron to have the noble gas configuration. Okay, ammonia. Ammonia's molecular formula is NH3. I kind of went through this quickly on water. I'll take a little bit more time with ammonia. Nitrogen has 5 valence electrons, and so it's going to have 5 valence electrons. Hydrogen has 1 valence electron, but you have 3 hydrogens, so it's going to look like this. You have 3 times 1. So you will have 8 total electrons depicted and your Lewis structure. And since hydrogen only likes to have one bond, and I'll talk about some bonding patterns coming up, because if you're wondering how in the world is she coming up with these Lewis structures, you don't necessarily have all the skills to do that yet. So I'm trying to go through it a little in a more detailed fashion so that when you actually get to drawing these Lewis structures of covalent compounds, it'll be more straightforward. So because hydrogen only has one electron, is only going to have one bond, nitrogen is going to be the central atom. So you can put nitrogen's 5 electrons around it. And then right now, nitrogen does not have an octet. It only has 5 electrons. So it needs 3 more electrons to come in here in bond. That's where hydrogen comes into play. So I'll draw hydrogens as X's, even though they're electrons. So with ammonia, let's see, we have done our 1, 2, 3, 4, 5, 6, 7, 8. We've drawn our 8 electrons. Now around nitrogen you have 2, 4, 6, 8 electrons. That's great. Around hydrogen you just have 2 electrons, and that's exactly how hydrogen wants it. Your bonding pairs, you could draw this as a line. I'm just going to put a rectangle around these so it's clear. So here I have 3 bonding pairs and 1 lone pair. I'm pointing this out because coming up we'll talk about molecular shape, and this can be very helpful. With water, you have 2 bonding pairs and 2 lone pairs. All right, so methane, we'll go through and do the same thing. Carbon is in group 4, so it has 4 valence electrons. So 4, and then hydrogen has 1 valence electron, but I have 4 of them. So I'm going to have 8 electrons in the structure of methane as well. So again, hydrogen is not going to be in the center because it only has 1 bond. So I'm going to put carbon, and I skipped ahead to this, sorry, that I would put 4 dots here, and then I would put the 4 X's from the hydrogens here. And that's what my Lewis structure would look like. Now with methane, you have 2, 4, 6, 8 electrons around carbon and 2 around hydrogen, each hydrogen. With methane, I have 4 bonded pairs around it, 0 lone pairs. Okay. How many electrons does each atom have around it? Hydrogen just has 2. All others, let's see, oxygen, nitrogen, and carbon have 8. Now I discussed a little bit already how H2O, NH3, CH4 are called molecular formulas. Molecular formulas are not the simplest ratio of atoms. So this is an important point to make. Molecular formulas are not the simplest ratio of atoms, whereas ionic formulas are. So molecular formulas indicate what atoms are involved, but not how they are connected. Electron dot structures not only tell what atoms are involved, they also give an idea of connectivity. So you couldn't figure out what the molecular shape of water, NH3, or CH4 looks like just from the molecular formula. That's why these electron dot structures are really helpful. Now, I talked a little bit about molecular formulas and ionic formulas. I want to go through a little bit more. Molecular refers to covalent bonding. And remember that covalent is non-metal to non-metal. So they're sharing here. And ionic formulas, the bonding is ionic, and typically you see this between a metal and a nonmetal or polyatomic ion. Now with this ionic bonding, you see electron transfer. So what I mean by that is electrons are lost, electrons are gained. There is no sharing with ionic formulas, ionic compounds. Molecular formulas, it's, let me state that with ionic formulas. Ionic formulas, it's the simplest ratio. With molecular formulas, do not simplify. You might say, well, how do I know whether or not to simplify? Again, look for the nonmetal to nonmetal. If it's nonmetal to nonmetal and you have something like this, H2O2, you say, oh, I really want to simplify that. That's really just HO. No, don't simplify it because hydrogen is a nonmetal and oxygen is a nonmetal. Whereas with an ionic formula like Zn2O2, well, zinc's a metal, oxygen is a nonmetal. I can simplify this. So I get ZnO. Okay. So I mentioned this briefly when I was going over the Lewis structures of water, ammonia, and methane. Bonding patterns. Elements in certain group numbers bond the same way each time. So instead of kind of relearning this each time, if you kind of memorize these bonding patterns, it can be a great help to you. So carbon is in group 4. The electron dot structure looks like this. In order for carbon to get 8 electrons around it, these X's are the potential bonding. The number of bonds it would need would be 4. 1, 2, 3, 4. Nitrogen's in group 5. The electron dot structure of nitrogen looks like this. So it has 5 around the nitrogen. It has 3 spots for bonds. So what you'll find is that the group number plus the number of bonds should add up to 8. 4 plus 4 gives you 8. 5 plus 3 gives you 8. Oxygen's in group 6. The electron dot structure looks like this. So it has 2 spots for bonds. Double check your math here. 6 plus 2 gives you 8. All right, halogens. Remember, halogens are in group 7. So I'm just going to pick chlorine, for instance. And let's see, we'll get 1, 2, 3, 4, 5, 6, 7. We just have 1 spot for bonding. So 1 bond. 7 plus 1 will give you 8. Now hydrogen is in group 1. That's what its Lewis or electron dot structure, Lewis structure looks like. So it just has 1 spot, so it's just going to have 1 bond. And again, remember, hydrogen is a minimalist. 1 plus 1 equals 2. It does not want any more than 2 electrons. All right, so those bonding patterns will help you later on. We're going to talk about polyatomic ions now. And polyatomic, if you think about poly means many, and atomic means atom, so many atom ions. So there are compounds that consist of ionic and covalent compounds like sodium hydroxide, which is also known as lye. Maybe you've had the opportunity to use it. I know I've had students who make their own soap. You know, it's kind of one of their hobbies, or maybe they remember their grandmother making their own soap. But while I have the opportunity, while we're talking about sodium hydroxide, if you ever find yourself, you know, with a clogged drain, or with, you know, maybe you want to make your own soap, you know, there are a lot of cool recipes out there. Be very careful with sodium hydroxide. It can cause a lot of damage. It can cause severe burns. So as long as you follow the safety instructions and you pay attention to that, you'll be fine. But sodium hydroxide is not like table salt. It can really hurt you. So it's an ionic compound that could, if it comes into contact with your skin, you could have a hole in your skin. And when I was an undergraduate student and I was taking chemistry, you would hear a lot of horror stories, like this. And so I'll tell you this one. I'm not sure if it was true. According to all of our graduate TAs, it was. But there was a student who was working with sodium hydroxide, and he went to the balance to weigh sodium hydroxide out. And he used a spatula, and he was using proper technique. And he had on his goggles, he had on everything he was supposed to, but it just happened. And by the way, these sodium hydroxide, it's like a little pellet. Trying to think of the best way to this. It's like a disc, a small disc. Kind of like a little bit bigger than the size of an Altoid, if you know what that meant is. But so he had measured out these pellets, and apparently one of these pellets fell into his sock. And so all throughout lab, he's working and he's trying to get his lab done. And by the end of lab, his foot really hurts. He takes off his shoe, he takes off his sock, and this sodium hydroxide has created a hole in his skin, and it's bleeding and very irritated, so he had to get that taken care of. But it's not really a stretch, like you hear these tall tales, but I don't think this is a made up. I think this really happened. But if you have the sodium hydroxide come in contact with your skin, it can definitely burn you. You would probably feel burning right away. It might have been that he was just so focused on his lab that he didn't feel it. So anyways, I'll get off my sodium hydroxide box now. Why I brought up sodium hydroxide is because we're talking about polyatomic ions. The formula for sodium hydroxide is NaOH. And hydroxide is a polyatomic ion. This is hydroxide right here. Hydroxide is like this. So polyatomic ions are charged particles containing two or more covalently bonded atoms. I want to stress, I know I've mentioned this in earlier lectures, that for polyatomic ions, you do not need to memorize these. We will provide the formulas for you. I'm going to give you some examples of polyatomic ions, but again, not for you to memorize. If you go to higher level chemistry courses, you definitely have to memorize polyatomic ions. So NH4 plus is ammonium ion, hydronium ion, H3O plus. We'll see this when we talk about acids and bases. Let's see. Acetate ion is C2H3O2 minus. Nitrate ion is NO3 minus. Let's see, and on the next page I have a few more. Nitrite ion. So you can kind of see how nitrate and nitrite are similar in name. They have a different formula, NO2 minus. Carbonate ion, CO3 2 minus. Sulfate ion, SO4 2 minus. Again, you don't have to memorize these. Chromate ion, CrO4 2 minus. Sulfate ion, SO4 2 minus. Phosphate ion, PO4 3 minus. So I have a question for you. Again, polyatomic ions you're not going to have to memorize, but just be aware of what they are and be able to recognize a polyatomic ion, like this question asks you. Which of the following compounds incorporates a polyatomic ion? Okay, C6H12O6. I don't see any polyatomic ions there. CO2, I don't see a charge. So if there was a charge, it might be a polyatomic ion, but there's no charge. like carbonate ion. Sorry about that. Carbonate ion, CO3, 2 minus. All right, K2SO3. This is a compound that involves the polyatomic ion. You have your cation, you have your anion. This is the anion. That's the polyatomic ion. Okay, and then SrBr2, strontium bromide, no polyatomic ion. There. Okay, so that concludes our lecture. Again, I'm going to repeat this. You probably are getting tired of hearing me say this. You do not need to memorize the periodic table or the polyatomic ions. So, until next time.